Have you ever wondered what Earth the size of a black hole would be like? Let's explore what would happen if Earth were the size of Ton 618, the largest black hole ever discovered. To start off, we need to comprehend just how immense an Earth the size of Ton 618 would be. Our current Earth has a radius of about 6,371 kilometers. Ton 618's black hole, by contrast, has a radius of roughly 195 billion kilometers. That means that Earth's radius would be about 30 million times larger than it is now. To help visualize this better, let's think in terms of volume. You could fit on the order of 10 to the power of 22 Earths inside of this giant hypothetical planet. That's 10 followed by 21 zeros. If that number is too abstract, consider this. It's more total Earths than there are stars in the observable universe, an utterly staggering quantity contained in just one planet. Even entire solar systems are small by comparison. The orbit of Neptune, the farthest planet in our solar system, is about 30 astronomical units in radius. For those of you who don't know, an astronomical unit is a form of measurement used in astronomy to describe distances within our solar system. 1 AU is defined as the average distance between Earth and the Sun, which is approximately 149 million kilometers. Ton 618's radius of 1300 astronomical units is about 43 times larger than Neptune's orbit. If this new Earth were centered where our Sun is, it would extend far beyond Pluto's path. In fact, Earth the size of Ton 618 could engulf the orbits of all of our planets many times over. It's as if you took the solar system and blew it up dozens of times. That's the scale of our hypothetical planet. Standing on such a world, the concept of a horizon and far side of the planet goes from the scale of kilometers to light days. Light itself would need about 15 days to travel from one side of this Earth to the other. So if you shined a flashlight on one side of the planet, approximately 2 weeks later it would reach the other end. When we scale up a planet to insane proportions, gravity becomes a formidable force. On Earth, gravity as we know it gives us a comfortable 1g at the surface. But what would gravity be like on our Earth the size of Ton 618? There's a couple ways to imagine this. If our gigantic Earth had the same density as the real Earth, its mass would be astronomically high. So high that it couldn't remain a normal planet. In fact, at that size, keeping Earth's average density would give it a mass on the order of 10 to the power of 47 kilograms, far beyond the mass of any black hole in the universe. That much mass in one place would collapse into a black hole instantly, no question about it. For context, Ton 618's black hole mass is only 1.32 times 10 to the power of 40 kilograms. Clearly a rocky Earth of that size and density is impossible. It would become a black hole many times over. So let's instead assume our hypothetical superplanet ends up with roughly the same mass as Ton 618, so that it just borders on being a black hole. Essentially, we're imagining Earth swollen to the event horizon size of Ton 618 and having a black hole's mass. What kind of gravity would that yield at the surface? A rocket launching off the face of this enormous Earth would need to achieve an almost light speed velocity to break free of its gravity. Nothing from our current technology could even come close. In fact, not even light can escape at that point, which is exactly why Ton 618 is a black hole. Scientists estimate that at the event horizon of Ton 618, the gravitational acceleration is on the order of 40 times that of Earth's gravity. That is extremely strong, enough to crush and kill a human immediately. We black out at around 5 to 8 Gs of force in fighter jets, so 40 Gs would be fatal. Any unprotected person on this mega Earth would be flattened. In fact, no life as we know it could survive 40 times Earth's gravity long term. The environment would be incredibly hostile just from the weight of the air and your own body. But gravity's effects don't just stop at weight. They also impact time itself. According to Einstein's general theory of relativity, a strong gravitational field slows down time, a phenomenon known as gravitational time dilation. Near an object as massive as Ton 618, time would pass at a significantly slower rate compared to far away in space. If somehow a colony of humans lived on the surface of this giant Earth, they would experience time differently from an outside observer. An hour on the surface might correspond to many hours or even days passing for someone far away from the planet's gravity. In the extreme case of being right at the event horizon, time would appear to nearly stand still to a distant observer. Clocks on the surface would tick slower and slower as you approach that ultimate boundary. This means if you tried to visit this Earth and then leave, you might find that while only a short time passed for you under its intense gravity, the rest of the universe aged significantly. It's a real-life and extreme version of the interstellar movie scenario. The closer you are to the enormous mass, the more dramatic the time dilation. Near the surface of our hypothetical planet, time might flow half as fast or less, depending on how close to a black hole status we are. The takeaway is that a day spent on this giant Earth could equal many days or weeks off-world. Your home planet would literally be in a deeper, slower time warp compared to the universe around it. Gravity and time become strange in this scenario. Our mega-Earth's gravity well is so deep that escaping it is nearly impossible, and even the flow of time is distorted. But what about other practical aspects such as living in such a world? Let's consider how light, heat, and orbits would work. On our normal Earth, we rely on the sun's light at a distance of 1 AU to sustain life. If Earth ballooned to the size of Ton 618, how could it receive sunlight? The sheer size of this new Earth forces a rethinking of our Earth to Sun relationship. Firstly, if we attempted to keep this giant Earth at 1 AU from a star like our Sun, there's an obvious problem. The Earth would be bigger than its orbit. A radius of 1300 AU means our planet would extend far beyond a 1 AU distance. To have Earth not swallow its own star, you'd have to place it extremely far away. We're talking about orbiting at thousands of AUs from the star, just so the star sits outside the planet's radius. Let's say our superplanet orbits some star at a safe distance like 2000 AU. One orbital year would last millennia, and the star's light would be incredibly dim. The intensity of sunlight drops off with the square of the distance. So if you were 2000 AU away instead of 1 AU, that's a decrease in sunlight by a factor of 4 million. Even at 100 AU, the sunlight is 10,000 times weaker than on Earth. This means on the surface of our giant Earth, daylight would look nothing like the bright days we know. Assuming it's similar to ours, the sun would appear merely as an extremely bright star in the sky. The illumination at noon might resemble deep twilight on normal Earth. Photosynthesis as we know it would be severely challenged. Most Earth plants could not survive on such feeble sunlight. They evolved for the intense solar energy at 1 AU. At 1000 plus AU, the few photons arriving each second might not be sufficient enough for plants to produce food. We'd likely need plants with radically different adaptations. Perhaps huge light gathering surfaces, extreme efficiency at capturing every bit of light, or maybe an entirely different energy source for ecosystems, like geothermal or chemical energy from the planet itself. With so little sunlight, our temperature would certainly be affected. A planet would normally be extremely cold. Our mega-Earth, however, might defy the usual expectations due to its own internal energy. If it had the mass of a black hole or even a fraction of it, it might radiate some heat of its own. But sustaining Earth-like temperatures from starlight at such distances seems impossible. In essence, sunlight would be scarce on this world. Day and night wouldn't be a usual cycle because if it rotates, parts of this immense planet would remain in darkness for centuries, simply due to its size and slow rotation. Overall, on our superplanet, life is bleak as we know it. The planet orbits far out and receives almost no light, plunging any surface into darkness and cold. But what would it take for humans to be able to live on a planet of this magnitude? If Earth suddenly grew to the size of Ton 618, the human race would face challenges unlike anything in our history. Gravity on the surface would be crushing. On a world with 5 times Earth's gravity, an average person who weighs 70 kilograms would feel like they weigh 350. At 40 G's of force, that becomes 2,800 kilograms of effective weight, basically like having an elephant sit on your chest. Clearly, unadapted humans couldn't even stand up. Our bones would break and our organs would collapse at just a few times the Earth's gravity, let alone dozens of times. To live on such a world, humans would have to evolve or engineer solutions. Over many generations, humans might become much shorter and stockier. Perhaps we'd be built very close to the ground to reduce stress, and our muscles would have to be far stronger relative to our body mass, with our bones being denser as well. The cardiovascular system would need to be extremely powerful to pump blood against the pull of gravity, maybe multiple hearts or a much higher blood pressure. Movement might be slow and deliberate. Quick jumps or running would be nearly impossible in heavy gravity. Buildings and cities would also have to adapt. Skyscrapers as we know them would be out of the question. Under strong gravity, they would collapse under their own weight. Architecture would favor squat, wide structures with strong support. Even a 2-story house might be an engineering challenge if gravity is extreme. We might live mostly in reinforced bunkers or even underground where the surrounding soil and rock can help bear the weight. Transportation across such a planet becomes a daunting prospect. On our normal Earth, we use cars, trains, and planes to travel relatively quickly. In high gravity, cars and trains would face much higher friction and require much more energy to move. Air travel might be nearly impossible. Wings that work in 1G won't lift in 5 or 10G without absurd speeds or enormous wing area. Now consider the distances on this super Earth. The planet's circumference comes out to about 1.2 trillion kilometers around. If somehow there were cities scattered on this gigantic globe, the distance between them could easily be billions of kilometers. Even 2 neighboring countries might be as far apart as Earth and Jupiter are in our real solar system. The concept of a global community might not exist. It would be more like many separate worlds on a single planet. Exploration would be a Herculean task. Consider that it took Magellan's expedition 3 years to sail around our modest Earth. To traverse a planet millions of times larger with only conventional means would take billions of years. For example, if you could drive continuously at highway speed of 100 kilometers per hour along the great circle of this Earth going non-stop, it would take nearly 1.4 billion years to circumnavigate at car speeds. Regions separated by just even 0.01% of the planet's circumference are still millions of kilometers apart. Even at extremely fast airplane speeds, those journeys would take thousands of years. Only by using some sort of near-instant transport, maybe quantum teleportation or some wormhole network, could the inhabitants treat their planet as a cohesive entity. While it's hard to get a perfect figure, some industry estimates suggest that from the dawn of commercial aviation to the present day, all planes combined have clocked a few trillion kilometers in total flight distance. So if you took every single kilometer ever flown by commercial airplanes and tried to spend it on circumnavigating this giant Earth once, you might, at best, manage only 1 or 2 loops around this planet's colossal 1.2 trillion kilometer circumference. Even the entire history of powered flight wouldn't let you do much more than circle this mega Earth a handful of times. What that means for civilization is that most people would never venture beyond a tiny fraction of the planet's surface. Entire continents, each perhaps containing the area of thousands of Earths, could remain isolated simply because they are too far away to reach. Different societies might develop unaware of each other, or only able to communicate via extremely long distance signals. So if you try to have a phone call with someone halfway around this Earth, you'd say, "Hello," and they'd only hear it 2 weeks later. A round-trip communication could be a month or more. Effectively, real-time communication across the globe would be impossible. Communication becomes more like how we communicate with interplanetary probes or a distant spacecraft, with significant delays. Parts of this planet could indeed remain forever unexplored. There might be majestic landscapes, perhaps gargantuan mountain ranges or endless oceans, that no human would ever come across as it's simply too far and too difficult to get there. Each locality would be like a self-contained world both culturally and ecologically. This assumes humans could survive at all, which as we discussed is impossible without extreme technological aid or biological modifications. The challenges of high gravity, vast distances, and slow communications would force humanity into a very different way of life, possibly clustered in arcology-like habitats designed to sustain life under crushing gravity, with technology doing the heavy lifting, literally. By now, it's clear that an Earth the size of Ton 618 is physically impossible as a traditional planet. Let's break down why using what we know from astronomy. Rocky planets have an upper size limit. Observations of exoplanets suggest that if a planet is more than 1.5 to 2 times the Earth's radius, it often begins to hold a thick atmosphere or becomes more like a mini Neptune. In other words, it's not a pure rock anymore. The largest confirmed rocky world, BD plus these numbers I'm not going to read, has about 2.2 times Earth's radius and 16 Earth masses. It's already pushing the boundaries of what we expected for rocky planets. Anything larger tends to accumulate hydrogen and helium gas during formation, swelling its radius further, but at the same time, those gases make it lower density, like a gas giant. So realistically, if you gather mass to make Earth Ton 618 sized, one of 2 things happens. The first thing that happens is that it could become a star. Long before reaching a black hole mass, the material would collapse under its own gravity and ignite fusion. You could get a supermassive star, although stars have an upper mass limit too. 66 billion solar masses won't form a single star. That's enough to make an entire galaxy of stars. So more likely, you'd end up with a cluster of stars or a quasi-stellar object, not just a single planet. The second thing that could happen is that it becomes a black hole. If somehow you dump enough mass into one place without letting it form into a normal star, you would get a black hole. Ton 618 itself likely formed from such a direct collapse in the early universe, bypassing normal star stages. There's simply no way to have that mass in a solid or even gaseous planet form. Gravity wins, and it collapses a core to a black hole, which then can grow. So an Earth-like planet of this size is a fantasy. It violates the rules of how materials behave under gravity and how planets form. The object would either not hold together as a planet, or ignite into a star, or just collapse. So as we return our thoughts to our normal-sized Earth, take a moment to appreciate its perfectly human-sized scale. Keep looking up at the stars in wonder, because in the vast theater of the cosmos, there are giants out there that make even the wildest imagination seem pale in comparison.